in a bit of a panic over the idea that Japan was going to overtake America in every possible way. And in particular, they were really freaked out about how the Fuji apple was going to defeat the Red Delicious, which is actually a good thing. Anyway, so there's a bunch of different things we might want to do with a text like this. The first thing we might want to do is identify the noun phrases. So we might want to say that the Fuji is a noun phrase, Red Delicious is a noun phrase, and so on. And we might also want to get the entire syntactic structure of the sentence. We might want to know what the subject of the sentence is, what the main verb is, and then the embedded sentence that says that's the actual quoted statement. We might also be interested in identifying the named entities. This one. We might also want to handle what's called co-reference resolution, where we want to know what pronoun, what noun or pronoun refers to. So it certainly won't get there on looks. We want to know that it refers to the Fuji and not to Red Delicious and not to America's apple heap. This problem is called co-reference resolution. We might also be interested in what's usually called canonicalization or lookification, where you want to link up the proper nouns to their sort of some canonicalized entry, maybe a Wikipedia database entry, maybe your own proprietary database. Who knows? And so in particular, we want to know that this is the Fuji apple, not Mount Fuji, not the company, and so on. Okay. Epic right now provides mostly the first two things I said, the parsing and then the named entity recognition, or the identifying the entities in the sentence. Okay. And Epic is treats NLP as a machine learning problem, in particular a structured prediction problem. And so the basic idea is we have documents come in, and then we have some black box, and then, or gold box, and then out comes some kind of structured object that is some kind of unit of linguistic analysis. That might be a syntactic parse, or it might be the list of all the named entities, or it might be the co-reference resolution telling you which pronouns refer to which nouns. Okay. So there's a couple of things that make NLP interesting and difficult as a machine learning problem. The first is that you have to deal with ambiguity, a lot of ambiguity. Natural language is famously ambiguous in a lot of different ways that you wouldn't even really expect, unless you really start to think about it and start looking at linguistics. So for instance, if you see the word bank, does it refer to a river bank, or does it refer to an institution? Or does it refer to a particular branch of a particular banking institution? It's a hard problem. It's called word sense disambiguation. There's also a lot of missing context, that some of which you can get from a source like Wikipedia, and some of it it's really hard to get without just being a person. So if I say something like, I walked into the building, the entrance was pretty, then you automatically know that that is the entrance to the building, but that's not at all obvious unless you know that buildings have entrances, and that probably that's the most salient aspect. The building is the most salient noun, so that refers, you get what I mean. Okay, and all this ambiguity and all this extra context gives rise to this problem of combinatorial structure, where for any given sentence, there are usually going to be exponentially many possible outputs, usually super exponentially. So there's usually going to be order of up to order of n to the n different possible output structures for any given sentence for a lot of these different problems. And so you have to be very careful in designing your algorithms to not, end up with something that takes factorially long, basically. Okay. Just as a fun example, this is a classic example of all the different ways in which natural language is ambiguous. If you've seen this example, don't say anything. So I Made Her Duck has at least 5, and I think closer to 7 or 8 different interpretations. Does anyone want to shout them out? Or you can try this. We can try audience participation, or we cannot do it.
I can only think of 2.
Okay, what are 2?
Well, I carved her duck out of wood, and I swung a bat at her.
Okay. Go ahead.
Dinner.
What? Yeah, you prepared duck for her for dinner?
You could be talking to a duck.
I made her duck. I like that. I hadn't thought about that one. Yeah, that's good. That's really good. Another one could be that you prepared her duck for dinner, not necessarily for her, but you stole her duck and then. Made can also be used in like a criminal justice perspective, where you made someone and you. I think that means that you identified them as like the person, right?
Right.
The guilty duck.
Yeah, the guilty duck.
There's also the mafia one.
Yeah, so it's kind of the opposite of the identifying them as the suspect. Yeah. Anyway, so there's tons of different analysis of just a 4-word sentence, right? And there's like very simple words. There's nothing special going on here. Anyway, so these are the kinds of things we have to wrestle with when we're doing natural language processing. Okay. So let's talk a little bit about some of the ways we actually build systems to actually do things. So this is named entity recognition. I'm going to talk about the task of named entity recognition for a while. The idea here is we have some kind of text, like in this tweet, Chez Panisse in Berkeley, California, a bowl of Churchill Burnet Orchard Page mandarins and medjool dates, and then some URL. And the goal of named entity recognition is to identify the people, the places, and the things, in addition to organizations and things like that. MISC is things. And so one more. So Adam Goldberg is a person. Chez Panisse in Churchill Burnet Orchards are organizations. Berkeley is, of course, a place. Great, thank you. And there aren't MISCs here. MISCs are things like 100 Years of Solitude, some kind of like a book. You look like you have a question.
No.
Okay. Okay, so let's talk about how we do this real quick. This is just some simple pre-processing. In Epic, we will assume that documents can be represented as strings, or maybe you just have a pointer as a file or URL or something. We have a pre-process method that will automatically extract the text and then tokenize it and sentence segment it, so that you just have the sentences and their tokens. And in addition, it will, if it points to a file or URL, it'll use the Apache Tika library and automatically pull out the text from a PDF document or a Microsoft Word document or anything like that. Tika is a really cool library if you haven't heard about it. Great. Okay, let's click through some more.
I'll click it.
Great, thank you. Okay, so once we have our text, we can load up an NER model automatically from the class path. We have models that you can just add as a Maven dependency, and it'll just show up for those of you who use the JVM ecosystem.
What is NER abbreviated?
Oh, NER is named entity recognition. So that's the task of identifying the people, places, and the things. That make sense? Great. Okay. So we can load up the model. Currently, we just have an NER model for English. Working on getting Spanish and German next. We have easy access to data for those languages. You can also tokenize, if you just have a sentence you want to work with, you can just tokenize it directly. And then you ask the NER model for the best possible sequence of which is just the best analysis. And it'll tell you almost 20 years ago, Bill Watterson, who's a person, walked away from location Calvin and Hobbes. So obviously Calvin and Hobbes is not a location. You can see why it would make that mistake, right? It said he walked away from something and then kind of looks like a location. But let's say we wanted to fix this. We're not happy with the off-the-shelf performance. So one thing we could do is we could annotate a bunch of data. We could go out and get a bunch of tweets, and we could pay people or Turkers are people, pay people to annotate them. And so we might say Jane Austen, my favorite authors are Jane Austen, Tolstoy, Moses, and that dude who wrote Calvin and Hobbes. Jane Austen, Tolstoy, and Moses, people, and the dude that wrote Calvin and Hobbes is this is a MISC. Okay, and so if we get a bunch of labeled data, we can improve our performance. We'll probably get this correctly right out of the box. We'll get the last example correctly immediately as soon as we do this. Okay, just probably click through this whole slide real fast. Great, awesome. Okay. Another choice, if we didn't want to annotate data, is we could go after what's called a gazetteer. Gazetteer is just a fancy word for a big list of words that are phrases that have some known meaning. So we might go to Wikipedia, which is a great source of data, and say, let's just get all of the comic strips for the off of Wikipedia, we'll just have a list of them, so that whenever we see a novel, whenever we see any comic strip, we'll just know what it is because everything's on Wikipedia. So we go down, we get Calvin and Hobbes here. And when we're building we can now build our own model. We'll have to use a new set. You'll have to retrain a whole model, but you can just pass in this gazetteer, which is just a dictionary, and it'll automatically use those as features. And assuming you do that, your performance will work. Just as a machine learning point, you have to be very careful when you build gazetteers. If they're really useful on the training set, then the system will use it and only it to make predictions. And then as soon as you see something new, you won't be able to use it. So for instance, if on your training set you only see, if your training set, your list of comics is perfect, then it'll learn to trust that if it's, if you, lost my train of thought. If you have a gazetteer and it's perfect on the training set in every possible way, then as soon as you go to the test set, if you see data that you, if you see a named entity that isn't in your gazetteer, it won't recognize that because it'll think the gazetteer is perfect. How could the gazetteer be wrong? And then you'll get the wrong answer. So anyway, you have to be very careful, but sometimes they can be very useful. Okay. So a little before, you probably saw semi-conditional random field. Semi-CRF. That stands for semi-Markov conditional random field. The name isn't terribly important. Basically, the idea is that a semi-CRF takes a text or any sequence and it breaks it up into a sequence of fields. So it's going to take, it's going to maybe group Chez Panisse and then Berkeley, California, and then it'll do the rest of it. One thing is that everything has to be a member of the field, so usually there's going to be some dummy not a field aspect. Okay. And the way semi-CRFs work is that they assign scores to spans of text. So for instance, you have a score for Chez Panisse. So the score for the previous example will be the score that Chez Panisse is a organization, plus the score that Berkeley, California is a location, plus the score that Ebola is not anything, plus the score of the so on. Okay. And the score can be broken down into a sum of individual feature weights. In NLP, we typically use indicator features, just 1-0 variables that are properties of the input string. So for instance, we might say that the score will be the weight of, it starts with Chez, it starts with a word that begins with capital C, it ends with a word that starts with a capital P, maybe it starts with sentence, which is a good indicator that it's probably a proper noun, and maybe we'll have some kind of function of the shape, so we'll say it's a sequence of 2 capitalized words. It doesn't matter what the actual content of the words are. And then maybe there's something that says it's 2 words long. Names tend to be 2 words long. Companies tend to be 1 word long, or maybe a little bit longer. Works of art tend to be very long. And then maybe we have a gazetteer feature. Okay, so that's how, no, that's great. That's how the semi-CRF actually does its job. And in Epic, we represent features in a very similar fashion to that. We use this thing called a featureizer domain-specific language, or DSL. That's just a fancy way of saying pretty syntax. So we can basically get the exact same set of features by doing things like the word of the beginning of the span, the word at the end of the span, the word before the beginning. So for instance, people, you'll often have titles at the beginning, for Mr., Mrs., Chairman, CEO, etc. Then the word 1 past the end, which is useful for similar reasons. Prefixes of the original word, so we want, all prefixes of the word Chez, say, C-H-C-H-E. Similarly, suffixes are very useful for telling the difference between companies and people. They tend to have, the ends of the words tend to look very different. And then the length of the span is also very useful. And And this is actually more or less exactly what the code would look like in Epic. So it's pretty simple to just write down what you think the features should be, and you can just inspect them and see what they are. Okay. Oh, gazetteer.
I'm sorry, what, that word was function that returns what?
Good question. So begin and end refer to the beginning word and the end word of the string. Word refers to the actual words in the underlying sentence. And these are just markers. So begin is actually not an integer. It's a marker that, when applied to this object, gives another object that under the hood we can add whenever we call it. It's basically a function. Whenever we call this function with a string in a position, or a sentence in a position, it'll give us the word at that position, basically. And so this says, so for any begin-end pair, this gives us the begin word, this gives us the word, the last word, this gives us the word before the beginning, and so on.
So those aren't scores, those are actually identifying words in a sentence or a sequence.
That's it, right, and it uses them as features.
Features.
When you have this plus symbol, do you not mean add or concat? Do you mean add as a feature? Or?
I mean this feature and also this feature and also this feature.
And plus is a function?
Yes, and Scala has operator overloading, so you can use pluses and minuses and things like that. Right. I find this useful. It tends to be much more compact than the typical imperative code that you would write for this, or if you wrote Java code for this, it would tend to be 2,000 lines long.
That's sort of like function chaining.
It's kind of fun. It's kind of these are like kind of little functions, and then this is kind of a combinator that tells you to combine two functions by concatenating their output. If that makes sense.
So what do you end up with after all of that?
You end up with a function that, when given a sentence and then a begin-end pair, will give you an array of features, which you can then ask for a weight. You can then look them up in a weight vector and give a score, basically. Yes, good question. Okay, cool. Right, and using your own featureizer is pretty simple. Once you have one of these objects, you can just say featureizer equals my featureizer, and then under the hood we'll just train with that featureizer instead, and it'll do its thing. Okay. So far we've not used any math at all, but of course machine learning is mostly about math. So I want to talk a little bit about how the math of structured prediction works out. I'm going to show a very simple adaptation of a machine learning algorithm that will go from a standard classification algorithm to a structured prediction algorithm. Yeah.
Wait, there's something I don't get.
Yeah.
Can you explain why prefixes is an important feature?
Sure. Well, first off, capital letter, very important for determining if something is a proper noun or not, right? And then it just turns out that there are certain patterns in language that I can't explicitly say because I don't actually know what they are, but maybe words that begin with X's tend not to be people's names very much, but are more likely to be, say, companies or names of drugs or something. Whereas a word that begins with C is more likely to be maybe a person's name overall, but maybe it could be something else. Does that make sense?
Okay, so yeah, that makes sense. Yeah, that makes a lot of sense. How about suffixes?
Mm-hmm. So suffixes, it's pretty common for company names, say, to be fancy looking, right? They end with weird suffixes, Xerox and things like that. Whereas people names tend to be more standard, I guess, in some ways. I mean, one good example I think is that often for like drug names or something, you end with things that look like Latin. So you end with UM and OM and IUM and things like that, and that's a good indicator. Yeah.
Are you able to weight the different features depending on your domain or other characteristics, or do you have a fixed weight?
So those are learned automatically from the data. You can't bias them in any particular way in the way we set it up right now. Yeah.
It's non-statistical. It's just looking for features. It's just and it's at the word per word level. That whole sequence analyzed one word or all the words in a sentence?
That's all the words for a particular span. That's all the features for a particular span. Can you go back?
So how do you do you just explore all the possible spans and decide?
Yeah. So there's a dynamic program. So there's a dynamic program that, which I'll get to a little bit. That given a feature function that scores spans, a score function that scores spans will output the best possible sequence of spans. And so if this feature function, all it has to do is give a set of features so that, give a set of indicators so that when I take the weights for each of those indicators and sum them up, that gives me a score. And the idea is that the higher that score is, the better of an indicator, the more likely that score, the higher the score is, the more likely you are to output a structure that has that span.
And what have you determined at that point about that span that is useful? How is it useful?
So you have a score that tells you how likely the span is to be a person, just a priori, or not a priori, a priori. Yeah, you just have some function that tells you that, and then you want to find the structure that the segmentation of the sentence into spans, that when you add up the scores for each of those spans, gives you the best possible score. Does that make sense?
Well, only if I know what I'm trying to determine in terms of what the various types of characteristics of spans are that I'd be looking for particular kinds of, I'm trying to identify the nature of a span by its characteristics, which are determined by the sort of a summing of the features about that span in order to determine something about that span.
That's right.
Such as name, which would be a combination of at least maybe one or two words or more and so on. So we're thinking of the span as an entity in and of itself with a summation of features that prove its characteristic that is useful to us in a particular thing.
That's right. That's right. That's right. So another way of thinking about this is if you're used to standard machine learning classification problems where you have you just think of each span as an atomic single classification. You run your logistic regression, softmax, support vector machine, whatever, and these are the kinds of features you probably use, I think, if you're building it independently. But you want to basically, you know that there won't be overlapping spans in the sentence, right? If Chez Panisse is a organization, then we know that Panisse, and then the next word, Panisse Berkeley, isn't going to be anything, right? And so we have to basically use an algorithm to exclude these sort of disallowed configurations.
And are you somehow progressing through the sequence like with n-grams, a sliding window of some sort?
Yeah, it's are you familiar with the forward backward algorithm by any chance, or Levenstein distance?
Hardly.
Okay. There's a standard dynamic program that this is based on that kind of looks like n-gram by n-gram. That's kind of how it does for increasing values of n. And then it just goes through for every possible.
Increasing or decreasing?
It doesn't matter. Yeah. It's great. Okay. Let's keep one more. Okay, one more here. Okay, so I think this might maybe make some of it make a little bit more sense. It may also just make it more confusing. Set it up as a standard machine learning problem. We have a x-y pair, where x is the data and y is the label. X is going to be a sentence, y is going to be the labeled version, so here's going to be a segmentation. And the goal is that we want to run our training algorithm such that for every data point x, y we have, we want that the score for x, y is bigger than the score for x, y prime for any other y prime. So this means that according to the labeling, we want the label, we want the training data version of this labeled sentence to be the best possible, the best score, have the best score for all possible segmentations. Okay.
Maximization.
Yes. Okay. And so we're going to set the score function up as a linear model, meaning that it's going to be the dot product of a weight vector, which we'll learn, with this feature function that we just talked about. Okay. In the Breeze library, you'll write that as score of xy is equal to w.t times fxy. That kind of looks like the math from before. Or we could just write that as w.fxy if you prefer. Okay. So our goal again is we want the score for xy to be bigger than score xy prime for all y prime. Okay. Which in practice means we want w.fxy to be bigger than w.fx, y prime for all. Okay. So geometrically, we can think about it like this. So the dot product basically is a function of the angle between two vectors, right? So w dot this y prime, fx y prime, is going to currently be bigger than the dot product between w and fxy. And that's because w and f point more in the same direction than fxy and w. Okay? So how can we make w point more in the direction of fxy? Well, the simplest thing we can do is that we can just, we can add fxy to w, and then that'll mean that w is going to point here now. And so that means that it gives us that the dot product, I'll finish my statement. All right. The dot product between fxy with plus fx, sorry, w and f plus fxy is dotted with fxy is going to be bigger than it was before we added fxy to w.
So do you normalize these vectors as well?
The algorithm we're going to use is no, does not. That actually works better. In practice, this is just a simple algorithm. Yeah.
But your analysis, doesn't it assume that f and f prime have to be the same height?
That's right. Yeah, so you think of these as a very large dimensional vector. It's very sparse. Where you have, for every feature, even the ones that you didn't, for every feature, you have a vector that is the length of the number of features you've seen. That's how big the feature vector is. That's the dimensionality. And then it's going to have for any data point xy, fxy is going to be a vector that has a 1 whenever we have the feature feature I, we're going to have a 1 there. And if we don't have that feature for this pair, we're going to have a 0. Does that make sense? A little bit. So they're going to be, we'll assume that they're all the same size vectors, basically. And we'll enforce that by we can enforce that by padding with zeros, basically. Okay. Was there another question? No. Okay. Okay. So the algorithm I just described is actually a known algorithm. It's called the Perceptron. It's a very old machine learning algorithm, but it is still actually used quite a lot today. It's from the 50s, I think. So the idea is we have two indices, which are basically alphabets that tell us which set of features we've seen and which set of labels we've seen. So, and then we're going to initialize a weight vector to some random small values, and we're going to make the dimensionality equal to the number of features in our training set. Does that make a little bit more sense, maybe? Okay, maybe starting to make. We'll keep going, I think. Okay, we'll keep going. And then we're going to iterate over our training data for some number of epochs. And we're going to, for every possible label, this is in the non-structured case, we're going to calculate the score of, we're going to compute the feature vector for that x and every possible label y, yy. And we're going to compute its score as the inner product, or the dot product, between the weight vector that it currently is and some feature vector, which is the vector for the features, which is going to be this 1, 0. Okay. Okay, so we're going to compute these label scores, and then once we do that, Right. We're going to have our label scores. We now pick the best possible label from these scores. And if what our current model thinks is the best structure, the best label, is not equal to the actual correct label, what we're going to do is we're going to add the weight vector. We're going to add the feature vector for the right answer to weights, and we're going to subtract the feature vector for the wrong answer. And so that's going to make it point more in the direction of the right answer and less in the direction of the wrong answer. Okay. And so you can imagine how if you keep doing this, you're going to slowly get more and more answers correct, because more and more of the time it's going to be pointing in the direction of the right answer rather than the direction of the wrong answer. Okay. So there's a problem if we want to do this in an NLP case. Remember at the beginning I said that there are combinatorially many possible labels. And in particular, the set of labels is going to change depending on the sentence. Longer sentences are going to have a different set of possible labelings than shorter sentences, just sort of trivially. And in particular, there's going to be super exponentially many of these in general. And so we can't possibly enumerate all of them explicitly. That's just going to blow up memory. Okay, so what can we do? So it turns out all we were using was the best. All we needed was to get the best possible structure out. We didn't need to be able. We didn't actually have to explicitly enumerate all possible structure. We just needed the best one. So how can we do that? Right. It turns out that there's a dynamic program, that's what I alluded to earlier, such that you can extract the best sequence automatic. There's a dynamic program that will allow you to extract the best structure given a feature function like the one we described before. And it runs in quadratic time. Okay. And so the structured perceptron algorithm now looks almost identical. The only difference is that we're going to call that dynamic program inside the inner loop. We're just going to outsource that to whatever. Okay. Yeah, go back. Okay, and this is, we don't actually use this algorithm in Epic. We use a more sophisticated version that's the generalization of logistic regression or support vector machines to the structured case. But this gives you a taste of what how the kinds of algorithms work. Yeah. Okay, I see a lot of confused looks. So, questions?
I have a question.
Okay.
You have weights and you're adding features for y and you're subtracting features for y best. Why is that not the inverse?
So y best is the answer that the current model thinks is the right answer. Y is the actual right answer, right?
Oh, okay.
So we want to point more in the direction of the actual right answer and not the wrong answer.
So y best isn't really the best, it's the best we found so far.
Yes, exactly. Yeah.
Is this, is a typical application part of speech labeling?
Mm-hmm.
That's what we're doing?
Yeah.
That's what you're kind of showing at the beginning.
Mm-hmm.
And this is a process, you gave that as an example of the problem or a problem. That's your example of the problem.
Yes.
And then that's sort of what you're showing us an example of processing. So when we're talking about these features and thinking what the result is, the result and the processing of the features is the alignment of parts of speech with the actual raw text. Am I thinking
that's
far
right.
off base?
That's right. The output. The thing we're looking for is the right sequence of part of speech labels for that particular sentence. And we do that by looking at individual features that tell us for each position indicators about that might help describe what kind of part of speech something is.
And the underlying mechanism is the vector model.
Yes.
Okay.
Yeah. Yeah. So pretty much everything, almost all machine learning, except for deep learning or neural networks, can be interpreted as linear models, where you just have vectors in some high-dimensional vector space, and you just add and do dot products. Deep learning adds just a little bit more of a wrinkle where it's a nonlinear function.
And when you, I'm sorry to, I want to make it back much, please excuse me if I'm doing too much interrupting, but when you're talking about the exponential aspect about the longer the sentence is, the more complexity there is, and therefore the more exponential the alignment becomes. What's the way of addressing that? You're not looking for an ultimate evaluation, but you're somehow able to shortcut.
So there's a dynamic program, right, that allows you to, so often in computer science, it's possible to find the right answer, even if you can't go through and manually check every answer individually.
You know what, this makes me think of exposing my lack of knowledge, but this reminds me of the Markov problem, where they realized they didn't need to examine the whole string. They're just taking, I mean, you're just making your determination in n-gram sequences, and as you do that, you're likely, your overall alignment is likely to be correct as it aligns in smaller segments sequentially. But that's not really what you're talking about.
No, I think there's definitely definitely a good connection there, which is that we're going to take this scoring of a complicated structure, this segmentation, arbitrary segmentation. We're going to define the score function in such a way that it breaks up into little pieces, so that they're more or less independent of one another. The little pieces.
If they're not n-grams, what are the little pieces?
They're lengths of sequence. We are breaking up the set. Yeah.
So you're not, but we don't refer to them as n-grams.
That's right. Usually when we think about n-grams, we think about for a fixed n, right? And so, but these can be different lengths.
Okay, so this is a variable length.
Yeah, you can think about this as sort of variable length n-gram kind of thing. Yeah. Yeah.
Does the package have a recursive neural net implementation?
No. So I could opine about neural nets. I will say this briefly, and except for language modeling tasks, neural nets actually haven't done very well in NLP as a rule. They've done okay, but they've never beat linear models. And since they're much more finicky to train and things like that, I prefer these. In speech recognition, which is actually very different from natural language processing, neural nets are really useful. But so far, no one's really gotten neural nets to work very well here, and I know how to implement these pretty well. So, okay. Right. So I'm going to talk a little bit about constituency parsing. This is the top half of this, where we want to extract the best possible structure, syntactic analysis of a given sentence, rather than labeling individual fields in some kind of flat way. So this is going to be a hierarchical cluster or structure. How many people happen to diagram sentences in middle school? A couple of you. Okay. So that's basically all this is. It turns out to be very useful for a lot of natural language, a lot of downstream tasks where you want to extract the content of a sentence because for translating between things, or trying to actually figure out what the meaning of the sentence is. The actual structure of the sentence is the syntactic structure of the sentence is very important for that. Okay. So let's go back to talking about ambiguity, like we talked about at the beginning. So if you have the sentence, we solved the problem with statistics. There are sort of two reasonable analyses of the sentence. The first is that we solved the problem using statistics, and the other analysis is that we solved the problem that statistics had, right? And they're both reasonable interpretations. You probably assume that we solved the problem using statistics. That's probably the right answer. But you can see why figuring out the difference between these two can be really challenging. We have to know that statistics is sort of more of a tool than it is a thing that has properties, right? It doesn't have problems exactly in the same way. And that's a pretty hard problem that's something that's very difficult to teach to a computer with just labeled training data. And so this is why parsing can actually be very difficult. Okay, so let's take a look at how we would do this. So we solve the problem with statistics. The problem is a noun phrase, right? It's a noun unit of it's a single noun, and we can solved is a verb, and they're going to combine to be a verb phrase that tell us that the sort of main verb structure in the sentence is solving the problem. And then with statistics is going to be a prepositional phrase that modifies the verb phrase to produce another verb phrase. So it tells us the manner in which we solve the problem. And then we combine the verb phrase with we, which is a pronoun or noun, and that gives us a sentence. And so once you have the structure, you can sort of ask questions like, what is the subject of the sentence? Well, it's we. What is the object of the sentence? It's the problem. And then what is the manner in which we did this thing? That tells it with statistics. Okay. Actually, let's skip this slide. We're going to do this in a similar way to we did the NER problem, where we're going to break out the problem into a sequence of decisions. And we want to classify individual spans according to the label, according to what kind of constituent we think they are, or maybe they're not a constituent at all. So, for instance, we'll look at a set of features like we did before. So we'll look at, say, the first word of the sentence, the first word of the span, and then the last word of the span. This is kind of just like we did before. And then we'll look at we'll look at the word to the right. So for instance, so this is useful because of tends to follow a noun phrase as a word. If you think about all the places where you see of pretty much anywhere, the word that comes before it will probably be some kind of noun or noun phrase. So useful information. Left context can also be really useful. So if you see the phrase estimates that we will eat 40% more apples this year, there's two possible analyses of this constituent. One is that it's a noun phrase, and the other is that it's a verb phrase. And the correct analysis depends entirely on what comes before. So if the word that comes before is a noun like he, then this is going to be a verb phrase, right? He estimates that we will eat 40% more apples this year. If on the other hand, it's something like he gives estimates that we will eat 40% more apples this year, then that's a noun phrase. And so that's another example of how ambiguity can be very challenging in natural language processing, but we can use context and other kinds of information to help resolve it. Okay. These correspond to linguistic notions. I don't actually want to talk about that. I don't actually know what I was going to say here. Oh, right. Let's just skip this.
Can you tell me what to stop?
Yeah. Okay. Anyway, so we built a parser that uses a very similar setup to the first part of the talk. And it turns out to be basically the best parser for every language except English out of the box. And it's within 1 or 2 points of being one or 2 points of being the best parser for English that you could download and use. And that's on the standard benchmarks. Once you get outside of the standard benchmarks, we're actually better than them typically. Them is called the Berkeley parser, which is a little bit confusing since I'm from Berkeley. Anyway, so you can see that kind of across the board we do very well on a bunch of languages. We're not very good at Arabic and French. The Arabic is unfortunate because most of the research gets funded by DARPA, and they really care about Arabic or something. Okay.
Well, yeah, so why wouldn't Arabic be in better shape?
There's a couple of different reasons.
There'd be a lot of interest there.
Yeah, we've looked at it. There's a couple of different things. One is that Arabic as a language tends to have much longer sentences than other languages.
It's a more difficult problem.
Yeah, but and for some reason this approach doesn't work as well on long sentences as the other approaches, which.
Well, what you described so far is that back to you brought up the idea of statistical that that you have rules and then you have statistical occurrence. And so when you're trying to decide what something is, because of ambiguity, it can be one thing or another. The rule will support both. And in order to make that determination of which rule is which is it more likely to say what's more likely based on statistical occurrence. But then when you try to do an alignment between two different syntactical systems, even though there's commonality, because there's a significant difference, you still have this layer of how you align. You've been able to, on both sides of the equation, you're able to statistically, you know what the rules are in either language, you're able to statistically determine what the likelihood of which rule is being applied. But when you need to correlate and align the two overlapping but not quite congruent systems, what's the system for doing that?
I'm not trying to totally follow. Let's take this offline.
Okay.
Yeah.
You got me curious when you said that on longer sentences, this method is not so good. I think going back 100 years or so, there were longer sentences in English, and perhaps like Shakespearean times and things of that sort. Did you look at the English longer sentences, and does it drop off then?
Yes. We also looked at that.
It does drop off?
Yeah, relative to how, so we are, it's not so much that we're worse at longer sentences, it seems, but that we're way better at shorter sentences and a little bit worse on average for most languages, or for English rather, and then Arabic in particular just has long sentences. There's another thing, which is that, I didn't go into this, but you know, we talked about using suffixes earlier. Suffixes in most of these languages is a really powerful indicator of the part of speech. So in English, if it ends with an S, it's probably a plural noun or a third person singular verb. If it ends in ing, it's probably a participle. Arabic doesn't work that way. Arabic, all the information that tells you the part of speech is in the middle of the word, which is kind of weird. Hebrew is the same way. And it's not 100% true, but it's pretty true. And so that's a lot of what's going on too, is just we have a silly model for that. Yeah.
Also on the longer sentences thing, is it because you have like longer spans, so you might be losing out some information?
Yes, that's I think one of the big reasons. Because we're only looking at the first and the last word, those are very useful for short spans for telling you the most syntactically salient words, but for longer sentences, the most important, syntactically important word tends to be in the middle. Yeah.
So what's your alternate for languages such as Arabic? I mean, this is one way to look at it. Have you guys figured out an alternate that would work better?
So I mean, you could use the approach that the Berkeley parser uses, which is a unsupervised learning approach. We've looked a little bit at marrying the two approaches to try to get the best of both worlds. We haven't gotten very far with that yet. We've gotten a little bit of games on English, and we haven't really played with Arabic much. I mean, 1 point isn't that much worse in the grand scheme of things. This is, yeah. Someone else was raising their hand. Yeah.
So the last 4 languages in your chart, do they all share the same issue with long sentences?
I actually haven't looked at the other languages. So Arabic and Hebrew share the same morphological thing where suffixes don't work very well. German, I think sentences tend to be a little bit longer. Actually, part of what's going on here is we ran our system out of the box. We spent less than a week getting these all working. The original author of the Berkeley parser spent some time on German and French, and so I think he tweaked the model just a little bit to be better for them. So I think that's why we're losing it on German and French. But I can't swear to that. Yeah.
Just to be clear, so you have the pre-decided features and you encode those in your feature detector. Or do you have an algorithm that automatically go over the wide set of features and kind of settle on the best feature detector for the language?
Yeah, so it's a good question. So we don't have anything that'll automatically search over this feature space. You can imagine, I mean, that's, we can write that down algorithmically. You can imagine an algorithm that could generate those specifications and then doing some kind of search procedure based on that. What we tend to do, at least when we build our systems, is we just throw tons and tons of features at things. So like this model has about 10 million features. And we just throw them all in there. Some of them are important, some of them aren't, and it doesn't really matter that much. You can use L1 regularization to then prune out the model to get rid of 99% of the features that don't matter. But most of the time, it turns out that in NLP, everything matters just a little bit, and so you almost always want more features. Yeah.
Parts, am I right in assuming that parts of speech labeling, that's what we mean when we talk about features predominantly in this case? Parts of speech labels?
No. Features are like they were before, the suffix and the prefix and the things like that. Or just the word itself.
Okay, so that's not parts of speech. But
Yeah.
those are, let's call those labels of your guys. So if it is features, it's absolutely important that those have all been determined for a language and are cataloged in statistics. In order for them to be recognized, training, those labels need to be determined, and then a statistical rendering of, so when you're doing statistical determination according to those labels, is there any degree of development or undevelopment with some of these languages versus the amount of work that's been put in another? In other words, are all of the features recognized and cataloged? And have the statistical and has the training been fully run so that we say we have adequate training for a determined catalog of features for each language?
I mean, we use a uniform set of features for every language. We use a uniform set of features for every language.
Oh, we do. And are they appropriate? Are they uniformly appropriate from language to language?
No, almost certainly not. So, for instance, we use suffixes for all languages as a feature.
And so
that's not very good for
features
Arabic.
are most likely. So one weakness for support of some of these languages is that there needs to be more work in identifying and determining features for those languages.
That's right. And we designed this in such a way that it should be fairly easy to customize it. Right? It's just adding another line of code.
That's interesting. I'd like to hear more about that. Eventually offline, whatever.
Okay. Yeah.
Does it make sense to integrate Epic and Book? Like, for instance, use an output of Book for Epic or vice versa?
So it's a good question. So Puck is another parser. It's actually, it uses the Berkeley parser underlying grammar rather than this approach. And that's just a property of how GPUs work. This approach doesn't work very well on GPUs. And I could go into more detail about that. But Puck currently only has a grammar for English, though it shouldn't be too hard to add the other grammars. And at the moment, there's nothing in Epic that depends on the parse directly, and so it wouldn't actually be very useful. But once we start doing things like co-reference resolution, which does depend on parses, then yeah, using Puck to make things much faster would be good. This runs at like 20 sentences a second on a typical CPU, and that's 20 times slower. And this is usually the bottleneck.
So you see that this doesn't have built in GPUs, that it's not very easy to test parallelize the algorithm? Or?
No, so it has more to do with sort of the memory coherence requirements that are in GPUs. So GPUs are really good at doing the same thing to a bunch of different data points. So SIMD, if you've heard SIMD before. And it's actually more than SIMD in some ways. It's actually like regularly structured data in addition to being the same instruction. And since the features tend to look totally different, you tend to be looking up feature weights in totally random parts of the feature vector, and that doesn't play nicely with GPUs.
So the weights don't fit into the cache?
They're about 10 megs. The entire weight vector is about 10 megabytes. So, no. It won't fit into the GPUs. GPUs only have like a couple of megs of L2 cache, and I think like one. So no, it won't fit. And GPUs they're kind of weird in general. Okay, yeah.
If you wanted to use a speech recognizer as a front end to this parser, is there an optimal way to do
I haven't done this at all. What do you mean exactly in terms of?
Well, the speech recognizer produced a set of sentences with probabilistic weights. You just apply it to all those outputs and then weight it somehow.
That's a good question. Yeah, we don't have a good answer for that yet. It is possible to write a dynamic program that, given a forest or a compactly represented set of sentences, is a like finite state automaton, to parse it and more efficiently than to parse each one individually. We don't have an algorithm for that. If you wanted to, if you had a bunch of different sentences and you wanted to see which one was the best using this information as a guide, we might have some that might be possible. So you get a score out for every. You can get a score of the for each of the sentence. Sorry, you can get a score that tells you sort of the amount of the sum of all possible scores for all possible trees that comes out for each sentence, for every parse of every sentence. And so you could use that score and compare them, and maybe that they might be calibrated in such a way that you can, say, well, this sentence seemed reasonably likely according to the speech recognizer. So did this one, but this one has a much better parse. That might be able to be something that can do, but I don't know. We'd have to play. Yeah.
So just to be clear, Epic does tokenization, name entity recognition, fast tagging, those parts, right?
And parsing.
And parsing, sure. Yeah, that's the main part. But it doesn't do like dependency parsing or co-reference resolution. So
no.
If you wanted to add those things in a Scala environment, what's your suggestion? What's the sort of easiest way to? Is there some? I've looked at some package out of Arizona, the Sista, that's like a wrapper for cont'd.
So cont'd out of the Stanford cont'd library is more mature than Epic. I feel safe saying that. It's been, they've been hammering on it for more than a decade now. And it is more feature complete, especially for English. They don't have, a Polish model or a Korean model, but our lab also has some co-reference resolution software out now that is in Scala, and it's the best. This co-reference system is the best in the world right now. It's Greg Durrett is the author on that. My goal is to get him to port his stuff to this framework, but I haven't convinced him to do that yet. Okay. Anyone else? Okay, great. All right, I'll do this slide real fast. Okay, so we have pre-built models for, I need to re-release them, but English, Basque, French, German, Swedish, Polish, and Korean. We're not publishing models yet for Arabic and Chinese.
What would that entail?
The big problem is tokenization. The big problem is tokenization. Arabic tokenization is difficult, and I haven't taken the time to figure out how to do it.
Does it require, is it a learning problem?
It can be cast as a learning problem. You can also use rules.
Would it always require a lookup, a dictionary?
It could use an approach kind of like we described here, of like a sequence model where you have features and scores and things, or you could use a dictionary. I don't know. I don't actually know very much about word segmentation.
So really linguistically, the features really need to be analyzed and determined fairly early.
For now, yeah. That's an active field of research to like automatically figure out how to build these kinds of things.
But a lot of research is actually available to give a lot of good information for how to go about it.
Sometimes it depends.
That needs to be implemented.
Yes. Okay. Parse speech tagging. It's very easy to train a part of speech tagger if you have the stuff to build a parser, so we have them for those. And entity recognition, we just have English right now. We're working on Spanish and German, I think. And then sentence segmentation, Currently, we just have a model built for English. Our support is okay for the other languages, just because other languages are actually easier to do sentence segmentation in than English. And then tokenization works for these set of languages. And that's only word tokenization. It doesn't do any kind of morphological segmentation or anything. Yeah.
I have a question around negation.
Okay.
I mean, based on my understanding, it's a complicated problem to solve and attempt. But I wanted to understand, does the system right now take into account any kind of negation?
It wouldn't come up in anything internal to the kinds of structures we're trying to produce. It's not like you see, I mean, you could imagine this, saying like Google is not a person and then learning Google is not a person, but we don't use any kind of thing like that. Negation is definitely when you start to do more semantic analysis than what we're doing. This is very surface level. Then negation obviously is very important, but we're not doing that yet. Yeah.
What would you say, you said you're not doing that yet, what would you say that this is absolutely the best thing for today?
All right, we have really good numbers for parsing Polish. I would say that we have sort of the best, I think the API is more friendly in general than JavaNLP. We are better at multilingual in general. We have a lot more models than they do. They're way more polished in English than we are. We're Apache licensed, so that can be very useful for a lot of you in the audience. JavaNLP is GPL, or you can pay them 10 grand. Which isn't that much money, I guess. I think the API is really good, and I guess I would say that. And and we're near state of the art on basically everything. So, yeah.
Could you talk just a little bit about the nature of your framework, how the structure as it exists does present some really good opportunity for doing the work to, for instance, the tokenization, the feature definition. Can you give me some clues to hang on to for how working with this framework will allow that work to progress in a productive fashion?
Sure. So basically, when I showed you the plus stuff at the beginning, you can imagine adding other things in there, right? And so you can just add in, you can just play with that, right? A lot of NLP is figuring out a good set of features. We have a pretty good default set of features for most things. Like I said, we're near state of the art at kind of everything that we try to do. But obviously, if your data is a little bit different, you have a little bit more information, or if you just want to bang on it a little bit harder than I did, you can probably get some gains if you just play with the features. It's supposed to be very easy.
So it would be flexible, adaptive, extensible?
Yes. Okay. That's the goal. Okay. Yeah, that's another thing it's good at, I think, is that it's very easy to change things without knowing too much about the internals.
Does it make sense to apply these models outside of natural language processing?
Sure, especially the semi-CRF, and then we also, which is the sequence segmentation. You can imagine doing that for any kind of time series data. It is geared towards discrete events right now, and not continuous events. But there's nothing other than that. There's nothing terribly natural language processing. Just you'd also need to define your own features because these are string features. But
what about image processing?
We don't have anything that, I mean, images are two-dimensional, right? They're not time series, so I don't have any dynamic programs or anything that is geared towards that. Yeah. Okay. Any other questions? Thank you.